Hi, everyone. Okay, so this is for your second midterm, the party number 2. And this time, I'd like to make it as a take-home exam with a given time limit. So what I'm going to do, I'm going to post this test material on the Blackboard on Wednesday at noon. So it's going to be 12 p.m. on Wednesday, and make it available until the Thursday at noon. So you have a total of 24 hours. I think that's the plenty of time to go through these 5 problems. So let me talk about more for the exam. Okay, so here we go. So I said that this is for midterm number 2. It's party number 2, also known as midterm 2. Okay, I already have all the problems available, my own, right? For me, and it's going to be uploaded on the Blackboard on Wednesday. And there are 5 different problems, and some of them are requiring to use some computer software like Excel and Prism software. So please make sure that you're using the computer and make those 2 softwares, Prism and Excel, available during that time. So it is going to be available between April 8th, Wednesday, 12 p.m. noon, to next day, Thursday, 9th at noon. So you have a total of 24 hours to solve those 5 problems. Okay, and it was initially said that the chapters 4, 5, and 6, I decided to just focus on 5 and 6 because chapter 4, we went through chapter 4 based on the textbook materials. We have different kinds of excitations like a uniform or the triangular shape, rectangular shape. There's a step functions. So there are different kinds of the excitation functions before we go on to the very random excitation. But it's more like a theoretical background, and we didn't go over any calculations or so. I just want you to focus on chapters 5 and 6. Okay, all right. And I said Excel and Prism, these 2 softwares should be available during this time to complete this take-home exam. Okay, again, this is open book, of course. Open material, any materials is open notes. And you're gonna use these 2 softwares. And yeah, at the end, so some of them you're gonna use Excel software, and I ask you to provide a table and the plots and the maximum value or something like that. So if you'd like to, save all information in the Excel file and send it to me, that's okay. But if you can just screen capture it and then make it into just one PDF, that's fine too. So either way is fine. I think the Blackboard, you can only upload one single file. So if you make it into one PDF and upload it on the Blackboard, that's totally fine. If you prefer to use the original data, like the Word format and Excel files, and capture in the screen captured your pictures and save it into PDF. I mean, the PDF or PPT, the PowerPoint or Excel, any kind of a format. But if you have more than one files that you need to submit, then you can email me, okay? So as long as you meet this deadline, the time, the Thursday, 12 p.m., that should be fine. Either you upload your file onto the Blackboard or send it to me via email, that's fine. Okay, so let's look at chapter 5 first. So chapter 5 is about numerical evaluation. So in the earlier chapter 1, 2, 3, and 4, we talk about how we can solve this differential equation, mu double dot cu dot ku is equal to p of t. So this is the very basic equation, equations of motion in structural dynamics. And we will talk about different things, what is m and c and k, how we can calculate the natural frequency, natural period, what about the damping. So we all talk about those backgrounds, and we also talk about how we can mathematically solve this differential equation. This is a second derivative differential equation with respect to time t. So we talk about those methods, and depending on the excitation and shape and the type of excitation, we talk about those in chapter 4. But there is a limitation that sometimes this P of t cannot be expressed in a certain type of mathematical formulation, like a sine wave or cosine wave. Those are really easy functions, and we can easily express in a mathematical formulation. But many times, like an earthquake or wind data measured from the sensors, it is really hard to make it into mathematical formulations. And then how can we apply those excitation to solve this problem? So that's how we ended up using this numerical evaluation. Numerical evaluation means we're going to apply some level of approximations to solve this equation. So hopefully we can have a very accurate enough data and responses throughout those approximate methods. So there were 3 different time stepping method. And by the way, one of the powerful thing for this numerical evaluation is we can apply it into random excitation, but also we can apply it into the nonlinear problems. And we have to think about these 3 things when we set up this numerical evaluation. The first one is a convergence and accuracy, and then stability. And some detailed informations are available in your textbook. So convergence means depending on the time step, this is time stepping method. So we're gonna set and split it into a certain time step and find out the response at each time step and move forward, right? So the response should be converging into the accurate number. So that's the convergence criteria. And then accuracy, of course, the final response and the answer should be accurate enough and compared to the exact solution. And stability, the solution and the procedure should be stable and then also make sure that the solution goes to converge to the exact solution. All right, so these are 3 criteria that we have to meet to and satisfy to use this numerical evaluation. So we studied 3 different approximations. The one was based on the approximation applying into the excitation. So this is called based on interpolation of excitation. Excitation is this P of t function, this P of t part. So I think I explained it in the class, but this is the regular and the original equation of motion. And in the earthquake engineering field, we kind of rearrange this equation. So when you divide it by m for everything, and then C over m and k over m, we can rearrange those terms into other parameters, which is the natural frequencies and the damping ratio. Then we can change our equation into this u double dot plus 2 times psi, the damping ratio, and omega n, that's the natural frequency, u dot, plus omega n squared, which is k over m, right, times u, which is equal to negative u double dot g of t. Okay, and these two equations are identical, but in a little bit different kind of expression. So as you can see, as I mentioned, that when you divide it by m for both sides, u double dot is the same. C over m is going to be equal to this. You can easily prove it, but this is equal to C over m. And this omega n squared is, of course, the k over m, right? Then this P of t and divided by m is going to be this. So this is going to be equal to P of t divided by m. So from there, P of t is the excitation, can be expressed as negative times m u double dot g. So this is double dot. So one of you asked me about the ground acceleration, the earthquake ground motion record for L central ground motion. The first column was a T, the 0.001, 0.2, or whatever, depending on the delta 2. And the second column, usually, this is the U double dot G, okay? Sometimes this is in G, sometimes this is in centimeter per square second. Anyway, this is the ground acceleration. So how can we have the P of T, the excitation? Well, minus mass times this whatever ground motion record here, that will be equivalent to the P of t. Okay. All right. So so the first approximation under numerical evaluation is we apply this approximation onto the excitation function. So you probably remember that A, B, C, D, and A prime, B prime, C prime, D prime to express this U and U dot at I plus 1th step. So I plus 1th step means when you just pick a random place at a certain time step, I, then these are going to be the future steps, displacement response and the velocity response. And we can make expressions for these two through A, B, C, D. These are all coefficients, and also A prime, B prime, C prime, D prime. So the first one is going to be U. The second one is U dot. Third one is P at ith step. And this is P I plus 1th step. Same thing here. I, U dot I, P I, and Pi plus 1. Okay, so if you know the current steps of displacement and velocities, those are these two. UIs are displacement response at a current step. And U dot I, those are the velocity response at the current step. Pi, this is excitation at the current step, and Pi plus 1, these are the excitation at one step further, right? Then we should be able to find out the displacement response and the velocity response. And when you keep going, then we can have a time history of all the responses. So table 5.2.1 and example problems 5.1, those two will cover this method. So go over this example 5.1. To solve the problem, you have to have the expressions for all these coefficients, a, b, c, d, and a prime, b prime, c prime, d prime. It looks simple, but you probably remember we have a really, really long table containing these expressions of these coefficients. So those are available in table 5.2.1. Since the take-home exam is open book test, I'm not going to provide those expressions. You can easily access those, the expressions in the table from your textbook, right? Okay, so this is the first excitation. The second one, the second method was central difference method. Okay, so this is the name of the method when we apply the approximation onto the time derivatives of displacement, which is v, the velocity and acceleration a, right? So the main equations that we had, this is from the derivation, u dot I, this is the velocity at the current step I, right? It is in terms of u I plus 1 minus u I minus 1 and over 2 times delta t. And then u double dot I, so this is the acceleration response. We express it in terms of displacement, ui plus 1 minus ui, the current displacement, and then plus ui minus 1, I minus 1 over delta t square. Delta t is a time step, so it is kind of a given, or you determine it before you jump into the problem. So based on this relationship, these are the key relationship. So we applied, so it is based on a finite difference approximation of the time derivatives of displacement, which is velocity u dot and u double dot acceleration. Okay, so based on this finite difference approximation of the time derivatives of displacement, then we develop these two relationships. From there, we were able to find out the future steps of the responses. And all their expressions are available in table 5.3.1. And example 5.2 is the problem using central difference methods. So you might remember that we have a half sine wave function for the p. So we should be able to find out all the values at a certain time step. Okay, so this p of t. And we apply this excitation into the single degree of freedom system, and we should be able to find out the responses with the actually four different methods, because we have two kind of variations under Newmark method. So this is the second method. The third one is the Newmark method. Okay, and there are two different methodologies depending on how you apply the approximation onto the acceleration. So one is the average acceleration method, and the second one is a linear acceleration method. So if you apply going through the acceleration variation, you just take the average value, that is called average acceleration, while you just apply the linear interpolation between the time step, that is called the linear acceleration method. And the table 5.4.1 1 describe and summarize all the kind of theoretical details about this method. Table 5.4.2 will provide all the expressions used in this method to solve the problem. And then example 5.3 is going to be the same problem using numeric method. One average acceleration, the other one is a linear acceleration. So if you are familiar with these three methods, then it should be fine. You should be able to get the answers for all the questions related to chapter 5. Okay, let's move on to chapter 6. Chapter 6 is about seismic design, calculation, and the response spectrum. So this is the basic information for the earthquake engineering, right? So chapter 6 about earthquake engineering. So earlier I mentioned that we are now using this a little bit different format of the equation of motion. U is equal to negative U double dot G of T. So this U double dot G is going to be the data coming from the sensors, the seismograph. And then U double dot is going to be acceleration, velocity, and displacement response of our single degree of freedom system. Okay, so in this chapter, we talked about the response, right? And we also talk about the ground acceleration, which is this U double dot G. We talk about response spectrum. 3 different versions, SD, SV, SA. So the basic idea is that response parameters are the maximum value from the analysis. So SD is going to be the maximum displacement, maximum velocity, maximum acceleration of the single degree of freedom depending on the different period. So typical graph looks something like this. These are the spectral value, like spectral acceleration or displacement or velocity. Oh no, sorry. That is for T. So this x-axis is going to be Tn, and this y-axis is going to be the response spectral values like SD or SV or SA. So when you fix the period of the structure, run the analysis of the single degree of freedom system and get the maximum value, that is going to be just 1 point here. And by changing those period, then you can have this multiple points. When you connect all those points, that will be the response spectrum. And in this class, we use Prism software. And I make a short video clip how to use that software to develop the response spectrum, so you can refer and go over that video clip again. And then how can we use this response spectrum and these spectral acceleration, velocity, displacement values in the real world problem? So example 6.2 and 6.3, again, I have separate video clips to solve these 2 example problems and put it on the blackboard so you can see it again to prepare this exam. So 6.2, I showed you how we use this response spectrum, and in that problem, we have a combined version of the response spectrum. So in one chart, we have all 3 values can be read. So, and then find out the maximum peak deformation, and also we should be able to find out the maximum bending stress using this equation, MC over I. So this bending moment is coming from the equivalent force times the height of that structural system, and C, the maximum value of Y, moment of inertia. So we should be able to find out the maximum bending stress. 6.3 is kind of interesting example problem. So you might remember that we initially had a certain size of the steel pipe. Designers said think that this is not enough, so he or she increased the size, but how that the increase of the steel pipe affects to the response value, response spectrum. And the conclusion was we had a benefit of using that larger steel pipe in terms of the peak deformation, but in terms of the acceleration, which is kind of critical to calculate the bending moment and the bending stress, it was even kind of a worse. So these two example problems will be good problems to exercise and then prepare the final exam. And then we also talk about seismic design procedures. So base shear calculation and this FI. So base shear is, let's say here we have a building structures against a certain ground motion earthquake here. The base shear is going to be the entire lateral forces. So when we think about the lateral forces for each floor level, let's say this is F1, F2, F3, then this V is going to be the sum of all these Fs, okay? So how can we get these numbers? Well, we cover the seismic design code, ASCE 7 and IBC code. All the required pages and the sections are available on the Blackboard. So we were able to find out the C sub S value. There are the upper limit and the lower limit of the C sub S, and W is basically the weight of the building. And these Fs are the lateral forces on each floor level. And there is an equation to calculate this. It's K times V, right? So so that we can distribute these entire base shear into the flow level. So if you're familiar with this, are confident solving these two problems from the textbook and several practice problems we went through during the class time for calculating this V and Fs, then that will be all for chapter 6. So again, this is the end of the review. So this test only covers chapter 5 and 6, and chapter 5, numerical evaluation, you should be able to run the analysis and find out the responses using Excel spreadsheet. And we went through multiple class times to cover all three methods, right? So you should be able to get the answers for the problems. Chapter 6, as I said here, response spectrum is one big concept, and examples 6.2 and 3 and the seismic design exercises would be a good starting point to prepare this exam. All right, so that's all. Enjoy your study and let me know. Feel free to contact me anytime. I'll be available most of the days, and if you'd like to set up a WebEx sessions so that we can, communicate face to face like this, and I can go over your questions, or we can go over the example problems together. If you have any specific questions, I can set up that session as well. But you can always shoot me an email to make an appointment, or just quickly, to ask the questions on the email. Then I'll be back to you as soon as possible. All right, thank you and enjoy. Bye.